Hello there, and welcome to the Sleepy Space Channel. Tonight, we turn toward Jupiter, the largest world the Sun ever made, and the sobering fact that nothing survives it. Every measure of this planet runs past what a living thing could endure. Its radiation would kill in minutes. Its pressure would crush any vessel long before it found anything solid, and there is no solid ground to find. Its winds blow for centuries, in a storm wider than the Earth. Its center is hotter than the surface of the Sun. Tonight we move through each of these in turn, from the storms at the top to the metal ocean far below, and we end somewhere unexpectedly peaceful. If you find these quiet explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to carry. There is nothing out there tonight that can reach you here. Settle in and let the giant stay where it is. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Far beyond the warm inner planets, past the rubble of the asteroid belt, the Sun has dwindled to a single brilliant point. Its light here is faint, only a small fraction of the warmth that falls on Earth. The cold is enormous, and the dark between the worlds is almost complete. And in that cold, turning slowly against the stars, there is a planet larger than every other world the Sun has ever made, combined. This is Jupiter, the king of the planets, and there is something sobering about a world built on this scale. Jupiter is the kind of place that does not bend to anything that might try to live there. It has no ground to stand on, no shore, no surface of any kind. It offers nothing solid beneath an arriving traveler, only an atmosphere that grows thicker and hotter and more crushing the further down one falls. Long before reaching anything that could be called a floor, a visitor would be flattened by pressure, cooked by rising heat, and finally pulled apart and folded into the planet itself. Nothing we know of could survive even the outer edges of this world. And yet Jupiter is not cruel, because cruelty would require it to notice us at all. It is simply enormous and old and entirely indifferent. To understand how large Jupiter truly is, it helps to set it beside the world we know. Jupiter holds more than 300 times the mass of the Earth. If every other planet in the solar system were gathered together into a single body, Jupiter would still outweigh that body more than 2 times over. It is the dominant planet by a margin that is difficult to picture. More than 1,300 Earths could be poured into the space it fills. Its face stretches roughly 11 times wider than ours from one side to the other. And still, for all that size, Jupiter is only about 1,000th the mass of the Sun. This is the first quiet lesson the planet teaches. As large as it is against the other worlds, it is small against a star. Jupiter sits in a strange middle place, far too grand to be called an ordinary planet, and far too slight to ever burn as a sun. It is a giant that never became something greater, and it has carried that almost greatness in silence for billions of years. Jupiter is made of almost the same ingredients as the Sun itself. It is mostly hydrogen, the lightest and simplest element, with a generous share of helium and only faint traces of everything else. There is no rock beneath your feet here because there are almost no feet of rock to be had. The planet is a globe of gas and fluid, growing denser toward the center, with no firm boundary between the air and the body of the world. In its broad recipe, Jupiter is a piece of the same cloud that made the Sun, shaped by gravity into a sphere but never lit. The planet turns faster than any other world in the solar system. Despite its tremendous size, a single day on Jupiter lasts under 10 hours. A point on its equator races around at many thousands of miles an hour, far faster than anything spins on Earth. This rapid turning has left a visible mark on the planet's shape. Jupiter is not a perfect ball. It bulges outward at its equator and flattens at its poles, pushed into a slightly squashed shape by the sheer speed of its spin. Even through a modest telescope, a careful eye can notice that the planet is a little wider than it is tall. That speed matters for more than shape. The fast rotation drives much of the weather we see on Jupiter, smearing its clouds into the long parallel bands that wrap the planet from pole to pole. It stretches storms sideways and feeds the powerful winds that race along its cloud tops. And far below, that same rapid turning helps stir the planet's interior into the engine that gives Jupiter its other titles, the strongest magnetic field and the most punishing radiation of any planet around the Sun. Jupiter sits about 5 times farther from the Sun than the Earth does. From that distance, the Sun appears as a small disk, and its warmth is thin. Sunlight at Jupiter is only a tiny fraction of what we feel on a clear day at home. By rights, a world that far out and that's starved of sunlight should be a quiet, frozen thing. Jupiter is not. It carries an inner warmth of its own, left over from its birth and from its slow, endless settling. And that hidden warmth drives storms that have outlasted every empire that has ever risen on Earth. The planet takes about 12 of our years to complete a single circle around the Sun. A child born when Jupiter sits in one part of the sky will be most of the way through grade school before the planet returns to that same place. Its orbit is gentle and nearly circular, so Jupiter does not swing wildly nearer and farther from the Sun across its year. It simply moves, steadily and slowly, along a wide and patient path that it has traced more than 300 million times since the solar system began. Around Jupiter circles the largest gathering of moons we know of anywhere among the planets. More than 90 moons have been counted so far, and the number tends to climb as our instruments improve. Most of these are small, irregular bodies, captured rocks and shards no larger than a mountain. But 4 of them are true worlds, large enough to have been seen through one of the earliest telescopes ever pointed at the sky. These 4 travel in stately order around their giant, and we will return to them later, because Jupiter does not merely hold its great moons. It heats them, cracks them, and bathes them in invisible fire. It is worth pausing on the simple fact of Jupiter's permanence. The storms on its face have raged for centuries. Its bands have wrapped it for as long as anyone has been able to look. Long before there were eyes on Earth to see it, before there were oceans, before the Earth itself had cooled into a solid world, Jupiter was already here, already enormous, already turning at this same dizzy speed. It formed early, perhaps first among the planets, and it has presided over the solar system ever since. When we look at Jupiter, we are not looking at something new. We are looking at one of the oldest finished things in our corner of the universe. That age and that scale are the reason Jupiter can seem so unforgiving. A world does not need to wish us harm to be a place where we could never live. Jupiter is hostile in the plainest way a place can be, by being built entirely out of conditions that life cannot meet. The pressures are beyond crushing, the radiation beyond lethal, the storms wider than our whole planet, the cold at the top giving way to furnace heat below. Every measure of this world runs past the edge of what a human body could endure. And so to ask what it would be like to stand on Jupiter is to ask the wrong question, because there is no standing, and there is no surviving. What there is, instead, is something to understand. Over the next couple of hours, we will travel inward through this planet, slowly and without hurry, from the bright banded clouds at the top all the way toward the strange center, where hydrogen itself becomes a metal and the temperatures climb past those of the surface of the sun. We will pass through the largest storm in the solar system and the most violent weather known to us. We will move out into the immense invisible structure of Jupiter's magnetism and into the belts of radiation that would end any living thing in moments. We will visit the moons that Jupiter torments, and we will end with the quiet, surprising truth that this enormous and unlivable world may be one of the reasons the Earth was ever safe enough for us at all. For now, simply let the size of it settle in your mind. There is a world out there in the cold, larger than 1,000 Earths, turning faster than seems possible, wrapped in storms and crowned in invisible fire, and it has been doing so peacefully and indifferently since before our world was born. It does not need us to watch it. But tonight, gently, we will. The first thing anyone notices about Jupiter is its face. Through a telescope, the planet shows a series of stripes, light and dark, running parallel to one another across the globe. These are the cloud bands of Jupiter, and they are among the most recognizable sights in the solar system. The pale stripes are called zones, and the darker ones are called belts, and together they give the planet the look of something carefully painted in cream and rust and brown. But there is nothing still about them. Every band is a river of moving air, and the whole face of the planet is in constant, restless motion. The bands exist because of the way Jupiter's atmosphere rises and falls. In the pale zones, gas is welling upward from below, cooling as it climbs and forming high, bright clouds of frozen ammonia. In the darker belts, the gas is sinking back downward, and we are able to see further into the warmer, lower layers, which appear in deeper shades. The planet sorts itself into these alternating lanes of rising and falling air, and because Jupiter spins so quickly, those lanes are stretched all the way around the globe into smooth parallel ribbons rather than scattered patches. Between each belt and zone runs a powerful wind. These are Jupiter's jet streams, and they blow in alternating directions, one band streaming east while the next streams west. The boundaries between them are lines of fierce turbulence, where opposing winds shear past one another and curl into swirls and eddies and small storms. The wind speeds along these streams are far greater than anything on Earth. Many of Jupiter's jets blow at well over 200 miles an hour, and some race faster still, sustained not for an afternoon, but for years and years on end. On Earth, our strongest storms eventually wear themselves out. They drag against mountains and coastlines. They run out over cold water, and the rough surface of the planet steals their energy. Jupiter offers its winds no such resistance. There is no land here, no shoreline, no ground to create friction and slow things down. A wind that begins blowing simply keeps blowing, fed by the planet's inner warmth and shaped by its rapid spin. This is why Jupiter's weather is measured not in days, but in decades and centuries. The planet has no way to stop its own storms. The colors of Jupiter are one of its lingering puzzles. We understand the broad layers of cloud well enough. Highest are the white clouds of ammonia ice. Below those lies a layer thought to be made of a compound of ammonia and sulfur, painted in browns and tans. Lower still, beyond easy view, there should be clouds of ordinary water. But the vivid oranges and reds that give Jupiter its warm, marbled appearance are not fully explained. They likely come from small amounts of other chemicals, perhaps sulfur or phosphorus, perhaps complex molecules built when sunlight and lightning break apart and rearrange the gases near the top of the atmosphere. These coloring agents are present only in traces, yet they tint the whole face of the world. For a long time, we could only guess how far down this weather reached. The bands might have been a thin skin over a calm interior, like a coat of paint, or they might have run far below. One of the surprises of recent exploration came when a spacecraft measured the planet's gravity carefully enough to weigh its winds. The answer was startling in the quiet way that good science often is. The jet streams of Jupiter are not shallow at all. They reach downward, roughly 2,000 miles, before they finally fade. The weather we see on the surface is the top of a system that plunges further into the planet than the entire width of many smaller worlds. That single fact reshapes how we picture Jupiter. The bands are not decoration. They are the visible tops of enormous flowing columns that extend thousands of miles into the body of the planet, all turning, all shearing past one another, all driven by heat rising from far below. When you look at the calm-seeming stripes of Jupiter, you are looking at the surface of a weather system with no real bottom, one that merges gradually into the strange fluid interior of the world. The bands themselves are not fixed forever. Over the years, they shift and change. A belt can fade and nearly vanish, its dark color washing out, and then return again sometime later, darkening back into place. The widths of the lanes drift. New storms bubble up along the turbulent boundaries, swirl for a while, and are either torn apart or swallowed by larger neighbors. Jupiter's face is recognizable from one decade to the next, but it is never exactly the same twice. The planet is always quietly repainting itself. Near the equator, the winds run especially fast and steady, in a broad current that circles the planet in the same direction as its spin. Moving away from the equator, toward the middle latitudes, the jets begin to alternate, one streaming the opposite way from the next, in a regular pattern of bands that holds across most of the globe. It is an orderly arrangement for something so violent, a kind of striped discipline imposed on chaos by the planet's relentless rotation. The same fast spin that flattens Jupiter's shape also combs its storms into these long, parallel lines. It is easy to forget the true size of what we are describing. A single one of Jupiter's bands is wider than the entire Earth. The swirls and eddies that appear as small ripples along a belt's edge are often larger than our largest oceans. When a modest white spot appears on Jupiter, and astronomers note it as a minor feature, that spot may be a storm broad enough to swallow our whole world without difficulty. The scale of everything here is so far beyond our own weather that our ordinary words for storms begin to lose their footing. And all of this moves with a slow grandeur that belies its speed. Because Jupiter is so large, even winds blowing hundreds of miles an hour take a long time to carry features all the way around the planet. Watching Jupiter over several nights, an observer sees the great bands slide gradually past, the storms drifting at their stately pace, the whole painted globe turning like an enormous wheel. The motion is ceaseless, but it is not frantic. It has the unhurried quality of something so large that even its violence unfolds gently to our eyes. This is the outer face of the giant, then. It is a world wrapped in endless parallel storms, striped in cream and rust, turning too fast for its size, painted in colors we cannot fully name, with winds that never tire, and weather that reaches thousands of miles toward the center. And somewhere in those southern bands, turning slowly against the flow, there is one storm, larger and older than all the rest, a single swirl of cloud that has been watched from Earth for longer than any nation now alive has existed. We turn to that storm next. Low in Jupiter's southern hemisphere, there turns a single storm so large and so lasting that it has its own name. We call it the Great Red Spot, and it is the most famous feature on any planet beyond our own. It appears as an enormous oval, ruddy and warm in color, set into the pale band around it like a stone set into cloth. It has been watched through telescopes for at least 3.5 centuries, and it may well be far older than our records of it. No other storm we know of has endured anything close to this long. The Great Red Spot is what is called an anticyclone, a region of high pressure where the winds circle a calm center. On Earth, our great storms are the opposite, low-pressure systems that spiral inward and quickly spend themselves. This storm spirals the other way and refuses to die. It rotates fully around once every 6 days or so, turning counter to the way our hurricanes turn, carried along the boundary between two opposing jet streams that feed it from above and below, like two hands rolling a marble between them. The size of the storm is difficult to take in. Even now, shrunken from what it once was, the Great Red Spot is wider than the entire Earth. For a traveler standing on our planet, the whole sky and horizon would fit inside this one storm, with room to spare. In centuries past, the observations suggest it was larger still, perhaps 2 or 3 times the width of Earth across its long axis. A storm that could have swallowed several of our worlds side by side has been turning in the same place on Jupiter for longer than the telescope has existed. Around its outer edge, the winds are ferocious. They blow at several hundred miles an hour, faster than any wind ever recorded on Earth, racing around the rim of the oval in a continuous stream. Yet the very center of the storm is strangely quiet, an eye of calm at the middle of all that fury. The violence lives in the circling walls, not in the core. It is a structure of contradiction, a place of the most powerful sustained winds in the solar system, wrapped around a still and silent center that has held its ground for generations. For a long time we could only see the top of the storm, and could only guess how far down it reached. Careful measurements of the planet's gravity finally gave an answer. The Great Red Spot reaches a few hundred miles below the cloud tops, which sounds shallow for something so wide, and in a sense, it is. It does not plunge nearly as far as the surrounding jet streams, which run thousands of miles down into the planet. But a few hundred miles is still far greater than the depth of any ocean on Earth, many times over. The storm is a flattened thing, far wider than it is tall, a great spinning lens of cloud pressed into the upper layers of the planet. Seen from above, the storm has a layered look, a series of nested bands of color circling inward toward the quieter center. The outer ring spins fastest, and the motion gradually slows further in, so that the storm is less a single whirl than a set of currents turning at different speeds around a calm middle. The clouds at the top of the storm rise higher than the surrounding atmosphere, lifted by the warm air welling up within it, so that the Great Red Spot stands slightly above the bands around it, like a low plateau of cloud. It is a structure of remarkable order, despite all its power, a single coherent thing that has held its shape and its place for longer than any storm should be able to last. The measurements also found that the base of the storm is warmer than its top. This warmth helps explain how the storm sustains its terrible winds, drawing energy from below and feeding it into the circling walls. The Great Red Spot is not simply coasting on momentum left over from some ancient beginning. It is being driven, fed, by the heat that rises endlessly from within the planet, which is why it has never run down the way an earthly storm always does. Why the storm is red remains one of Jupiter's open questions. The coloring is thought to come from chemicals lifted high into the storm, where sunlight alters them and tints them in warm shades. The exact recipe is uncertain. The color also varies over time, deepening to a strong brick red in some years and fading toward a paler salmon in others, as though the storm were slowly breathing through changes we do not fully understand. We can describe the red. We cannot yet fully explain it. What we can see clearly is that the storm is shrinking. Over the past century, and especially in recent decades, the Great Red Spot has grown smaller and more rounded. Once a long oval, it has been drawing inward toward a more circular shape, losing width along its longer dimension. No one is certain what this means. The storm may be entering a long decline that will eventually see it fade away. Or it may be passing through one of many slow cycles, due to gather itself and grow again. We are watching a single storm change across human lifetimes, and we do not know how the story ends. Part of what keeps the storm alive is that it feeds on its smaller neighbors. From time to time, lesser storms drift close to the Great Red Spot and are caught in its circulation. Some are torn apart along its edges. Others are absorbed whole, their energy folded into the larger system. The Great Storm is in this sense a kind of slow collector, pulling in the disturbances around it and adding their strength to its own. Each small storm it swallows may help it hold on a little longer against the forces that would wear it down. It is worth resting for a moment on the patience of this thing. The Great Red Spot was already old when the first people pointed a lens at the sky and noticed it. It was turning through the years of sailing ships and handwritten letters, through the rise and fall of cities, through every change our world has known in the modern age. Generations of astronomers have been born, have studied it across their careers, and have died, while the storm simply continued. It owes us nothing and notices nothing. It has been turning in the cold southern bands of Jupiter the entire time, indifferent to every eye that has ever found it. And it is only the largest of Jupiter's storms, not the only one. The same planet that holds this centuries-old giant is dotted with lesser storms, some of them nearly the size of Earth themselves, scattered across the bands like a field of slow whirlpools. To picture Jupiter truly, you have to imagine not one great storm, but a whole world of them, turning at every latitude, merging and fading and reforming, all of it driven by the heat below and combed into lines by the planet's restless spin. We turn now to that wider company of storms, and to the strange weather they hide. The Great Red Spot has a smaller cousin. Some years ago, 3 separate white storms that had each been turning for decades drifted close together and merged into a single larger oval. In the time since, that merged storm changed color, shifting from white to a reddish tone, much like the Great Storm itself, though smaller. Observers began calling it the Lesser Red Spot, a second ruddy oval trailing the first across the southern bands. It was a chance to watch, almost in real time, how a great storm on Jupiter might be born from the joining of smaller ones. White ovals like those are common across the planet. They are cooler, higher storms, their tops made of bright ammonia cloud, and they can persist for years or decades before fading or merging. They tend to gather at particular latitudes, riding the boundaries between the bands, and they drift slowly along those lanes, like beads on a wire. Some are nearly the size of Earth. A feature an observer might note as a small, bright knot along a belt could hold a storm broad enough to cover our entire planet. Alongside, the white ovals are darker storms, sometimes called brown barges. These are warmer, lower features, openings of a kind that let us see further down into the planet, and they appear as long, dark ovals set into the lighter zones. They too can last for years. Between the bright high storms and the dark low ones, Jupiter's middle latitudes are crowded with circulating systems at every scale, a slow traffic of storms that drift, collide, merge, and dissolve across the face of the world. In the southern hemisphere, a chain of white storms sometimes forms a row so regular that it has been likened to a string of pearls. Each pearl in the string is a separate rotating storm, and the whole arrangement circles the planet together, evenly spaced, turning in unison. The number of storms in the chain changes over the years as some fade and others appear. It is one more example of the strange order that Jupiter imposes on its chaos. Storms lining up like a row of lamps along one of the planet's hidden currents. Downstream of the Great Red Spot lies a wide region of turbulence. As the great storm plows along its band, it leaves a churning wake behind it, a field of swirls and ripples and smaller eddies stirred up by its passage. This turbulent region is itself larger than many planets, a roiling zone where the air never settles. The storms here are short-lived and constantly changing, born in the disturbance of the giant's wake and torn apart again within days or weeks. Even the calm-seeming bands of Jupiter are, on close inspection, alive with this restless motion. The great bands themselves can transform in ways that surprise us. On occasion, one of Jupiter's prominent dark belts has faded almost completely, its color washing out until the planet appeared to have lost an entire stripe. For a time, the belt seemed simply to vanish, leaving a broad, pale gap where a bold band had been. Then, months later, the belt returned, darkening back into place as the high white haze that had hidden it cleared away. These fades and revivals show that even Jupiter's most permanent-looking features are part of a living system, capable of disappearing and reforming on timescales we can watch within a single year. All of this weather is driven by two great sources of energy working together. From above, the faint sunlight warms the very top of the atmosphere a little. From below, and far more importantly, the planet's own inner heat rises steadily through the layers, carrying energy upward into the clouds. It is this rising warmth from within that powers Jupiter's storms and keeps them turning long after any sunlight-driven system would have died. The planet is, in effect, heated from the inside, and its weather is the visible churning of that escaping heat. The rising heat does not climb evenly. It moves in great columns and plumes, lifting warm gas upward in some places and letting cooler gas sink in others. Where warm gas rises and cools, clouds form and storms gather. Where gas sinks, the skies clear and we see further down. The banded pattern of Jupiter is the large-scale signature of this overturning, sorted into lanes by the planet's spin, and the countless storms are the smaller knots and curls within that endless circulation. It is humbling to consider how much of this weather we still cannot fully predict. We can describe the bands and name the great storms, but the detailed behavior of Jupiter's atmosphere remains beyond our complete understanding. We cannot say exactly when a belt will fade, or when two ovals will merge, or how long the Great Red Spot will last. The planet keeps a great deal of its weather hidden below the clouds, in layers we are only beginning to probe. Every close look has brought surprises, and there is every reason to expect that more are waiting. What emerges from all of this is a picture of Jupiter not as a single painted ball, but as an entire world of weather, more active and more enduring than anything on Earth. Storms the size of planets drift across its face by the dozen. Bright ovals and dark barges ride its currents. Chains of storms circle in formation. Belts fade and return. And through it all, the great storm turns in the south, the oldest of them, presiding over a planet that never, for a single hour, stops moving. Below this restless surface, stranger weather still is hidden, and it is there that we turn next, to the lightning and the falling slush of Jupiter's hidden storms. When the first spacecraft passed Jupiter and turned to watch its night side, it saw flashes in the dark. Jupiter has lightning, as Earth does, born in towering clouds where charges build and discharge in sudden bursts of light. For a long time, this seemed a familiar thing, a touch of the homely amid the alien. But the closer we have looked, the stranger Jupiter's lightning has proven to be, and it has become one more way that this planet refuses to behave like our own. On Earth, lightning clusters near the equator, where the sun beats down hardest and warm, moist air rises into thunderheads. On Jupiter, the pattern is reversed. The lightning gathers toward the poles and grows rare near the equator. The reason lies in where the planet's heat comes from. Because Jupiter is warmed mostly from within rather than from the distant sun, the equator is not the favored place for rising storms. Instead, the churning that builds thunderclouds is strongest in the higher latitudes, and so it is there, near the top and bottom of the world, that the flashes are most common. There is also a kind of lightning on Jupiter that does not match anything we knew before. High in the atmosphere, far above where ordinary water clouds can form, flashes appear in a layer where the temperatures should be far too cold for the usual kind of storm. The answer seems to lie in ammonia. Mixed with water, ammonia can stay liquid at temperatures that would otherwise freeze it solid, acting something like an antifreeze. This lets strange, high storms form where they should not, and produces a shallow lightning that flickers in the upper layers of the planet. The same chemistry appears to produce something stranger still. In the most violent updrafts, water and ammonia are thought to combine into soft, slushy hailstones, which researchers have nicknamed mushballs. These form when powerful storms carry water high enough to freeze, where it gathers a coating of ammonia-laden slush and grows heavy. Once heavy enough, the mushballs fall, carrying their water and ammonia far down into the planet before they finally warm and break apart. This slow rain of slush may help explain why parts of Jupiter's upper atmosphere seem oddly short of ammonia. The planet has been hiding it below, locked in falling hail. It is a quietly remarkable picture. Somewhere in the upper layers of Jupiter, in storms larger than our continents, slushy hail made of water and ammonia is forming and falling through the clouds, sorting the planet's chemistry as it goes. We cannot see this happening directly. We have pieced it together from the planet's lightning, from its missing ammonia, and from careful study of how its storms behave. It is a reminder that even the weather of Jupiter holds processes with no clear match anywhere else we have looked. The greatest surprises, though, waited at the poles. For most of the history of our study of Jupiter, we saw the planet from near its equator, and its poles were edges we could not see clearly. The bands that wrapped the planet break down at high latitudes, and what lay at the very top and bottom of the world was unknown. Only when a spacecraft flew over the poles directly did we finally see them, and what it found was something no one had quite predicted. At each pole sits a cluster of giant cyclones arranged in a near-perfect geometric pattern. At the North Pole, a single central cyclone is encircled by a ring of others, set evenly around it like the points of a polygon. At the South Pole, a similar central storm is ringed by a smaller number of companions in their own regular arrangement. Each of these cyclones is a storm broad enough to span a continent. They turn beside one another, packed close, their edges nearly touching, and yet they hold their formation rather than merging into one. This arrangement is strangely stable. One might expect such enormous storms, crowded so tightly together, to spiral into a single larger system before long. Instead, they have kept their polygonal pattern, each cyclone holding its place in the ring, turning in formation around the central storm. We are still working to understand exactly how this order maintains itself. It appears to be a natural balance, a pattern that emerges on its own from the physics of many large storms packed together, but the details are not fully settled. It is order arising from violence, beauty arising from chaos, at the top and bottom of the largest planet around the Sun. The poles also glow. Above these clustered storms, in the upper reaches of the atmosphere, hang the brightest and most enduring auroras in the solar system, curtains of light that never fully fade. We will return to those lights later, because their story is tangled up with the planet's magnetism and with one of its tormented moons. For now, it is enough to know that Jupiter's poles are crowned twice over, once by their rings of giant cyclones, and once by these permanent fires of light far above. So the weather of Jupiter, the more we learn of it, only grows stranger and more layered. There is lightning that gathers at the wrong end of the planet. There is a shallow flickering in clouds that should be too cold to form. There is slush made of water and ammonia falling unseen through the storms. And there are crowns of giant cyclones, locked in geometric formation, turning quietly at the poles beneath sheets of permanent light. All of this is the upper world of Jupiter, the part we can see and study from a distance. To understand the planet truly, though, we have to leave the clouds behind and begin the long fall inward, toward a place where the very idea of weather and of ground comes apart. That fall is where we go next. Imagine letting yourself sink into Jupiter from the top of its clouds. The first thing you would learn is that there is no floor waiting for you anywhere. Jupiter has no surface in any sense we would recognize. There is no line where the air ends and the planet begins, no shore, no crust, no solid ground at any depth. To fall into Jupiter is to fall through gas that simply grows thicker and hotter and more crushing without ever becoming something you could stand upon. The journey down is a journey with no destination of the usual kind. At the cloud tops, the cold is severe. Temperatures there sit near 140 degrees below zero on the Celsius scale, far colder than anything on Earth. The pressure, by contrast, is gentle, much like the pressure in our own upper atmosphere. If you began your fall here, the early part would feel almost like drifting through a freezing, hazy sky, with ammonia clouds streaming past and the great bands stretching to every horizon. But this mildness would not last. With every mile downward, the weight of the gas above you grows, and the pressure and temperature begin their long, relentless climb. We have actually done this once, with a machine rather than a traveler. A small probe was released into Jupiter's atmosphere and sent plunging into the clouds to measure what it found. It fell by parachute through the upper layers, sending back its readings as the pressure mounted around it. It survived for about an hour, descending roughly 100 miles into the planet. By the end, the pressure around it had risen to more than 20 times the pressure at Earth's sea level, and the temperature had climbed well above the boiling point of water. Then the probe fell silent, overwhelmed, crushed and cooked by conditions that were still only those of Jupiter's outermost skin. That is the part worth holding on to. The probe that gave its existence to measure Jupiter reached only the thinnest outer layer of the planet, 100 miles into a world tens of thousands of miles across. It was as though something had dipped the very tip of a finger into an ocean and then been destroyed. Everything below where the probe died is far beyond the reach of any machine we have built, a region we understand only through careful reasoning about how gases behave under pressures we can scarcely create on Earth. Continue the fall in imagination then, past the point where any real probe could survive. As you sink, the gas around you grows steadily denser. The hydrogen that makes up most of the planet is thinning and warming above you, and thickening below, until at some point the idea of a clear boundary between gas and liquid stops making sense. Under the enormous pressures within Jupiter, hydrogen enters a state where there is no real difference between the two. There is no surface of an ocean to splash into, no moment where you pass from air into sea. The gas simply becomes a fluid by degrees, smoothly, and without any line to mark the change. This is one of the genuinely strange things about Jupiter. We are used to worlds with clear layers, a solid ground beneath an ocean beneath a sky. Jupiter has none of these neat divisions. It is a single body of matter that changes its character gradually with depth, from thin, cold gas at the top through a thickening warm fluid towards stranger states still further down. To ask where the atmosphere ends and the planet begins is to ask a question the planet does not answer. There is only the smooth, continuous thickening of hydrogen as you fall. The heat by now would be tremendous. Within a few hundred miles, the temperatures rise past anything that could be called survivable, climbing into the hundreds and then the thousands of degrees as you sink further. The pressure grows in step, mounting until it would flatten and fold any structure, any vehicle, any living thing, long before the truly extreme layers are reached. There is no slow suffocation here, no gentle ending. The descent into Jupiter is a descent into being crushed and heated out of existence, gradually but without mercy, by the simple weight of the world pressing down. And still, in imagination, the fall would continue for a very long way. Jupiter is so large that even after sinking 1,000 miles, you would have barely begun. Below would lie thousands of miles more of ever denser fluid hydrogen, warming toward a glow, pressing toward states of matter we will explore in a moment. The scale of the interior is part of what makes the planet so unforgiving. It is not a thin shell of atmosphere over a solid world. It is depth upon depth of crushing fluid, mile after mile of it, all the way down toward a center that lies tens of thousands of miles beneath the clouds. It can be a strangely calming thing to picture, this endless, gentle fall through a world with no ground. There is nothing to hit, no sudden stop, only the slow thickening of the medium around you and the rising warmth and weight. The violence of Jupiter's interior is not the violence of collision. It is the quiet, patient violence of pressure, of a world so massive that simply being inside it is enough to undo anything that tries. The planet does not need cliffs or oceans to be lethal. It only needs its own great weight, applied without end, the further down you go. Below the layers we have described lies something stranger than fluid hydrogen, a place where the most common element in the universe is squeezed until it behaves like a metal. That layer is the true engine of Jupiter, the source of its magnetism and its invisible fire. We have fallen as far as ordinary matter can take us. Now we turn to the ocean of liquid metal that fills the center of the world. Far below the fluid hydrogen, where the pressure has climbed to a level almost impossible to picture, the most common element in the universe begins to behave in a way that has no equal anywhere near us. Hydrogen, squeezed hard enough, stops acting like a gas or an ordinary liquid at all. Its atoms are pressed so close together that their electrons come loose and begin to move freely, the way they do inside a piece of metal. The hydrogen becomes a liquid that conducts electricity. This is liquid metallic hydrogen, and it fills the greater part of Jupiter's interior. To make hydrogen into a metal takes pressures around 2 million times the pressure of the air at Earth's surface, along with temperatures of many thousands of degrees. These are conditions we can barely create on Earth, and then only for a flicker of an instant in specialized laboratories. Inside Jupiter, they are not rare or fleeting. They are the steady, everyday state of most of the planet's volume. Beneath a layer of ordinary fluid hydrogen lies this enormous body of liquid metal, thousands of miles thick, surrounding the center of the world. This metal ocean is the largest such structure in the solar system, and it is the engine that gives Jupiter much of its power. As the planet spins, this electrically conducting fluid churns and circulates, and a moving, conducting fluid generates a magnetic field. The same basic process happens in the molten center of the Earth, but on Jupiter, it operates on a scale beyond comparison, driven by a far larger body of conducting fluid and by the planet's very fast rotation. The result is the strongest magnetic field of any planet around the Sun, and we will follow that field outward in a moment. There is another strange process thought to occur within these layers. Where the fluid hydrogen gives way to the metallic form, helium no longer mixes easily with the hydrogen around it. Instead, it gathers into droplets, and those droplets, being heavier, sink slowly toward the center like a kind of rain. This slow fall of helium through the planet's interior releases a little additional heat, and it may help explain why the upper atmosphere of Jupiter seems somewhat short of helium compared to the Sun. Far below the clouds, in a place no eye will ever see, it may quite literally rain helium, the droplets settling downward through the metal for thousands of miles. It is one more way the interior of Jupiter behaves unlike anything in ordinary experience, governed by pressures and temperatures that turn even the simplest elements into something new. The temperatures continue to climb the further in we go. Near the center of Jupiter, the temperature is thought to reach somewhere between 20,000 and 35,000 degrees on the Celsius scale. That is hotter than the visible surface of the Sun. The center of this cold and distant planet, so far from the Sun's warmth, is in fact one of the hotter places in the solar system outside of the Sun itself. The pressure there climbs to tens of millions of times the pressure at Earth's surface, a weight that defies any ordinary sense of the word. For a long time, the simplest picture imagined a clean center for Jupiter, a compact ball of rock and metal at the middle, perhaps several times the mass of the Earth, wrapped in all those layers of hydrogen. Careful measurements of the planet's gravity have complicated that tidy image. The data suggest that Jupiter does not have a sharp, well-defined center of heavy material at all. Instead, the rock and metal appear to be partly dissolved and spread out, smeared across perhaps half the radius of the planet, blending gradually into the metallic hydrogen above, rather than sitting in a distinct ball. This idea is sometimes called a dilute or fuzzy core, and it is one of Jupiter's quieter surprises. It suggests that the planet has no clear middle in the way we might expect, no firm center you could point to and call the core. Instead, there is a gradual thickening, a slow enrichment of heavier elements as you move inward, with no sharp line anywhere. The very concept of a center grows soft and uncertain the closer you try to look. Jupiter may simply fade toward its middle, denser and hotter by degrees, without ever offering a solid kernel at the end. How the planet came to have such a smeared center is not settled. One possibility is that it formed this way, with its heavy elements never fully gathering into a tight ball. Another, more dramatic possibility is that long ago, when the solar system was young, another large body struck the forming Jupiter and disrupted whatever neat core it had begun to build, mixing the heavy material outward into the layers above. If that happened, then the fuzzy center of Jupiter would be the long-settled record of an ancient collision, still preserved in the structure of the planet billions of years later. We will probably never see any of this directly. No light escapes from the center of Jupiter. No probe could ever reach those depths, and our knowledge of the interior comes from indirect signs, from the planet's gravity, its magnetism, its shape, and the slow ringing of its whole body in response to its storms. From these clues we have built our picture of layers, of the fluid hydrogen, the metal ocean, and the soft, uncertain center. It is a picture assembled by reasoning rather than by sight, and it is still being refined with every new measurement. What it leaves us with is a sense of strangeness that grows rather than fades. The center of Jupiter is hotter than the face of the Sun, pressed under tens of millions of atmospheres, made of hydrogen turned to metal and heavy elements smeared into a haze. There is no ground there, no clear core, no place a thing could ever be. It is a region defined entirely by extremes, sealed forever beneath thousands of miles of crushing fluid. And from the churning of that metal ocean rises the planet's true crown, an invisible structure so large that the bright striped ball we see is only a small thing at its center. That invisible giant is where we turn next. The churning ocean of liquid metal at the center of Jupiter does something that reaches far beyond the planet itself. It generates a magnetic field, and that field is the strongest produced by any planet around the Sun. At its source, far within the planet, Jupiter's magnetism is roughly 20,000 times stronger than the magnetic field of the Earth. Even at the cloud tops, far from the metal ocean that makes it, the field is many times stronger than anything our own planet produces. Jupiter is, in a sense, an enormous magnet wrapped in storms. A planet's magnetic field does not simply sit at its surface. It reaches outward into space, carving out a region around the planet where the field holds sway and shapes the behavior of charged particles. This region is called the magnetosphere, and Jupiter's is the largest single structure in the solar system, apart from the Sun's own far-reaching influence. It is so large that, if our eyes could see it as a glowing shape in the night sky, it would appear several times wider than the full moon, despite lying hundreds of millions of miles away. An invisible structure around a distant planet would loom larger in our sky than the moon that lights our nights. On the side facing the Sun, Jupiter's magnetosphere is compressed by the steady stream of particles flowing out from the Sun, the solar wind. Even compressed, it reaches outward, 1,000,000 miles or more before the solar wind finally pushes it back. Where the two meet, there is a kind of standing shock front, a boundary where the solar wind is abruptly slowed and diverted around the planet's magnetic domain. Jupiter plows through the solar wind like a great ship, throwing up an invisible bow wave millions of miles across. On the side facing away from the Sun, the magnetosphere streams outward into an immense tail, drawn out by the solar wind the way a windsock trails in a breeze. This magnetic tail is so long that it stretches across hundreds of millions of miles, reaching outward far enough to brush the orbit of Saturn, the next planet beyond. A spacecraft traveling from Jupiter towards Saturn can pass through the faint remnants of Jupiter's magnetic tail along the way. The influence of this one planet, invisible and silent, spans a portion of the solar system larger than the distance between many of the inner worlds. The field is not perfectly aligned with the planet's spin. It is tilted somewhat, and its center is offset from the center of the planet, so that as Jupiter rotates, the whole immense magnetosphere wobbles like a slightly bent top. Riding within this tilted, spinning field are sheets and rings of charged particles, great invisible currents that circle the planet and pulse with its rotation. The entire structure turns with Jupiter once every 10 hours, an unimaginable expanse of magnetism sweeping around the planet faster than the hands of a clock. Trapped within this magnetic domain are enormous quantities of charged particles, and here, the magnetosphere becomes something more than an invisible curiosity. The field captures electrons and ions and accelerates them, holding them in great belts around the planet and driving them to tremendous energies. These are Jupiter's radiation belts, and they are the most lethal environment of their kind around any planet. We will turn to them and to their danger in a moment, because they are central to the question of why nothing survives Jupiter. For now, hold the scale of the thing in mind. It helps to step back and picture the whole arrangement. At the center sits the planet, the bright striped ball with its great storm, 11 times wider than Earth. Around it, unseen, stretches a magnetic structure so enormous that the planet within it is like a single seed at the center of a great, invisible fruit. The magnetosphere dwarfs the planet that creates it, just as the planet dwarfs its moons. Layer upon layer of scale opens outward, each one larger than the last, until the visible world of Jupiter is only the small glowing core of something far greater that we cannot see at all. This is one of the recurring lessons of Jupiter. So much of what makes the planet extraordinary is hidden from ordinary sight. The metal ocean is sealed within. The fuzzy center can never be seen. And the largest structure of all, the magnetosphere, is entirely invisible to the eye, detectable only by the instruments we send and by the radio glow it produces. The bright marbled ball in the telescope is real, but it is only the part of Jupiter that happens to catch the light. The greater part of the planet's presence is silent and unseen, reaching across the dark for 100 million miles in every direction. Within that silent domain, though, there is something far from gentle. The same magnetism that builds this immense and invisible structure also gathers and accelerates particles into belts of radiation, fierce enough to kill in minutes and to ruin any machine not heavily shielded against them. The invisible giant has a lethal interior. We turn now to that radiation, to the killing light that fills the space around Jupiter. Within Jupiter's magnetic domain, the planet holds belts of radiation more intense than those around any other world near the Sun. The same magnetic field that builds the great invisible structure also traps charged particles, electrons and ions, and accelerates them to enormous speeds. Many of these particles are driven to nearly the speed of light, swarming around the planet in great invisible rings. This is the radiation that gives Jupiter much of its lethal reputation, and it is the clearest answer to the question of why nothing survives here. To understand the danger, it helps to think in terms of dose, the amount of radiation a body absorbs. A dose that would be dangerous to a human is measured in modest numbers of a unit called the rem. Near the orbit of Jupiter's innermost large moon, the radiation delivers something like several thousand rem in a single day. That is many times a fatal dose for a person, absorbed not over a lifetime or a year, but in well under an hour. A human placed unshielded in that region would receive a deadly dose almost at once, long before any other hazard of the planet could reach them. The intensity falls off with distance from the planet, but slowly. Farther out, near the orbit of the great ice-covered moon, the daily dose is still far beyond what a person could survive, though it takes a little longer to accumulate. Beyond that, near the largest moon, the levels finally drop to something a well-protected traveler might endure for a time. And at the orbit of the outermost large moon, far from the worst of the belts, the radiation is mild enough that this distant world stands as the one relatively safe place in the entire Jovian system. Safety here is measured purely by distance from the planet's invisible fire. The radiation is just as hard on machines as on living things. The charged particles tear through electronics, corrupt their memory, and gradually destroy the delicate components that any spacecraft depends on. To send a probe into this environment is to send it into a storm that will slowly kill it, no matter how careful we are. The engineers who build such craft must armor them as if for war. One orbiter that studies Jupiter closely carries its most sensitive electronics inside a thick box of titanium. A radiation vault with walls about a centimeter thick, built to shield the craft's brain from the worst of the bombardment. Even with such armor, survival in the belts is a matter of careful planning rather than brute endurance. That same orbiter flies a path that loops over the planet's poles and dives close only briefly before swinging far out again, threading between the most intense regions of radiation rather than lingering in them. Every pass through the inner system adds to the damage, and the mission is, in part, a slow race against the radiation's gradual ruin of the spacecraft. The planet wears down its visitors. The only question is how much can be learned before it does. The particles that fill these belts come from more than one source. Some are drawn in from the solar wind and trapped by the field. But a great deal of the material comes from the planet's own moons, and above all from the innermost large moon, whose constant volcanic eruptions feed charged particles into the space around Jupiter. The magnetic field gathers this material, accelerates it, and binds it into the belts. In this way, the planet's radiation is fed in part by the very moons that orbit within it, a system that powers its own danger from the inside. There is a strange beauty to one consequence of all this. As the trapped electrons spiral around the magnetic field lines at nearly the speed of light, they give off radio waves. Jupiter therefore glows brightly in radio light, shining in wavelengths our eyes cannot see. To a radio telescope, the planet is one of the brightest objects in the sky, its glow betraying the invisible swarms of particles racing around it. The same radiation that would kill an astronaut announces itself across the solar system as a soft radio hum, the sound, in a sense, of the planet's lethal halo. It is worth holding the full picture gently in mind. Around Jupiter, in a region we cannot see, charged particles race at nearly light speed, delivering doses that would end a human life in minutes and slowly destroying even our best armored machines. This is not a danger of storms, or pressure, or cold. It is a danger woven into empty space itself, into the seemingly clear volume around the planet, made lethal by magnetism and motion. There is nowhere to hide within the inner belts, no shelter that empty space can offer, only the steady, invisible rain of particles. The radiation also works upon the surfaces of the moons themselves. As charged particles strike the icy faces of the nearer moons, they slowly alter the chemistry there, splitting molecules apart and building new ones, and darkening the surfaces over the ages. The leading and trailing sides of a moon can come to look different from one another, weathered unevenly by the particles that sweep past them. On the ice-covered moons, this constant bombardment may create new compounds at the surface, and were those compounds ever carried down into the oceans far below, they could matter for the chemistry of those hidden seas. The same radiation that forbids life on the surface may, in this roundabout way, help deliver ingredients to the places where life might just be possible. Even Jupiter's killing light leaves its quiet mark on everything within reach. And yet, like so much about Jupiter, this lethal radiation also produces something extraordinarily lovely. The same particles that fill the killing belts are funneled down toward the planet's poles, where they crash into the upper atmosphere and set it glowing. There, far above the clustered cyclones, they create the brightest and most enduring auroras in the solar system, curtains of light that never go out. The killing light and the beautiful light are, in the end, the same light. We turn now to those endless auroras and to the tormented moon that helps to feed them. On Earth, the northern and southern lights come and go. They flare when the sun sends a gust of particles our way, and they fade when the sun is quiet, dancing for a while, and then vanishing. Jupiter's auroras do neither. They are the most powerful auroras in the solar system, hundreds of times more energetic than our own, and they never fully switch off. Above each of the planet's poles, in light our eyes cannot quite see, there hangs a permanent ring of glowing atmosphere, a crown of fire that has been burning without pause for as long as we have been able to look. The reason Jupiter's lights are so steady lies in where their energy comes from. Earth's auroras depend almost entirely on the sun, so they rise and fall with the sun's moods. Jupiter's auroras are driven mostly by the planet itself, by the tremendous energy of its own rapid rotation, which sweeps the magnetic field and its trapped particles around once every 10 hours. This internal engine never stops, and so the auroras it powers never stop either. The sun adds to them, but it is not their master. Jupiter lights its own poles, from its own spin, on its own schedule. Much of the material that feeds these lights comes from a single moon. The innermost large moon of Jupiter is the most volcanically active world in the solar system, and its eruptions throw great quantities of gas into space. Jupiter's magnetic field sweeps up this gas, strips it of electrons, and spreads it into an enormous donut-shaped ring of charged particles that circles the planet along the moon's orbit. This ring is sometimes called the plasma torus, and it glows faintly with its own light, an enormous circle of electrified gas wrapped around Jupiter, fed continuously by a single restless moon. From this ring, particles spiral down along the magnetic field lines toward the poles, and where they strike the upper atmosphere, they make it glow. The connection between the moon and the planet is so direct that the moon leaves its own bright mark in Jupiter's auroras. A glowing spot appears in the auroral ring at exactly the point where the magnetic field lines passing through the moon meet the planet, a footprint of light that moves as the moon moves. The other large moons leave fainter footprints of their own. The auroras of Jupiter are, in part, a map of its moons painted in light at the poles. These lights shine most brightly in the ultraviolet, and they also blaze in X-rays, the high-energy light usually associated with the hottest and most violent places in the universe. Jupiter's poles pulse with X-ray light in slow, regular beats, a rhythm we are still working to fully explain. To the instruments that can see these wavelengths, the poles of Jupiter are among the brightest features of their kind anywhere among the planets, glowing steadily in forms of light that on Earth we associate with the sun's most energetic outbursts. The planet wears this high-energy crown all the time, without effort, as a simple consequence of its spin and its moons. The amount of material involved is large by any ordinary measure. Something like a ton of gas every second is stripped from the volcanic moon and fed into the space around Jupiter. Second after second, year after year, this steady supply pours into the magnetic field, replenishing the glowing ring and feeding the auroras and the radiation belts alike. The moon is slowly being eroded into the system around it, its volcanic breath becoming the planet's invisible halo and the fuel for its endless lights. It is a strange kind of giving, one world's eruptions becoming another world's crown. There is something quietly moving in the permanence of these lights. The auroras of Earth are precious to us, partly because they are rare and fleeting, gifts of a few special nights. Jupiter's auroras have no such scarcity. They have been glowing at its poles without pause through every moment of human history and for countless ages before, and they will go on glowing long after. No one needs to be there to see them. They simply burn, steady and bright in their unseen colors, fed by spin and by a volcanic moon, indifferent to whether any eye ever finds them. To picture them is a peaceful thing, even knowing the lethal radiation that lies behind them. High above the clustered storms at each pole, far above the slush and the lightning, there hangs a ring of soft light that never goes out, turning slowly with the planet, marked with the moving footprints of distant moons. It is one of the loveliest things in the solar system, and almost no one will ever see it directly. It is a beauty that exists entirely for itself, in a place that would kill us, above a world that does not know we are here. The moon that feeds this crown is itself one of the most extraordinary places we know of. A world turned inside out by Jupiter's gravity, its surface remade again and again by fire. To understand how a single moon can supply a planet's auroras, we have to look closely at that burning world and at the other great moons that share its fate. We turn now to the moons that Jupiter holds and heats and harms. There is a fact about Jupiter that quietly changes how we should understand all its weather. The planet gives off more heat than it receives from the sun. Measured carefully, Jupiter radiates into space roughly twice as much energy as the faint sunlight that reaches it at its great distance. This is not because it has any hidden fire or any process like the burning of a star. It is because the planet carries warmth of its own, left over from its making, and renewed by a slow inward settling that continues to this day. Some of this internal heat is simply the warmth of birth. When Jupiter formed, an enormous amount of material fell together under gravity, and falling material releases energy. The young planet was far hotter than it is now, glowing with the heat of its own assembly. Over the billions of years since, it has been cooling, radiating that primordial warmth slowly out into the cold around it. Even now, after all this time, it has not finished. The center of the planet still holds a great store of heat from the era when it first came together, leaking outward by degrees. There is a second source as well, and it is still at work. Jupiter is very slowly shrinking. Under its own immense gravity, the planet contracts by a tiny amount each year, and as it contracts, the squeezing of its interior releases energy as heat. This gentle, continuous shrinking adds to the warmth flowing out of the planet. The amount of contraction is small, far too little to notice from one century to the next, but spread across the whole enormous body of Jupiter and across the ages, it is enough to keep the planet glowing with its own internal warmth. This inner heat is what truly drives Jupiter's weather. On Earth, the sun is the engine of nearly all our storms. Sunlight warms the ground and the seas, and that warmth lifts the air and stirs the winds. At Jupiter's distance, sunlight is too weak to do such work alone. Instead, it is the heat rising from within the planet that powers the storms, lifting warm gas upward through the layers, driving the great overturning that sorts the planet into its bands. Jupiter's weather comes not from the sky above, but from the depths below, fed by warmth that has been escaping since the planet was young. This explains a puzzle that might otherwise trouble us. How can a planet so far from the sun, so starved of light, have the most active weather in the solar system? The answer is that Jupiter does not depend on the sun for its storms. It is heated from inside, like a pot warmed from beneath, and so its weather is fierce regardless of how faint the sunlight grows. The same would be true if Jupiter drifted even farther from the sun. Its storms would still rage, fed by the warmth of its own slow cooling, indifferent to the distant star. Because of this warmth, Jupiter glows softly in the infrared, the light of heat. To an instrument tuned to such light, the planet shines with its own glow, rather than merely reflecting the sun, brightest where its warm interior shows through gaps in the clouds. The dark belts, where we see down to lower and warmer layers, glow more brightly in this heat light than the high cold zones. Seen in infrared, Jupiter is not a sunlit ball, but a self-luminous world, faintly aglow, with the warmth still seeping out of it after all these ages. The cooling will continue for a very long time. Jupiter loses its warmth so slowly and holds so much of it that it will go on radiating more than it receives for billions of years yet to come. The planet is in no hurry. Its great size, which makes it so lethal in every other respect, also makes it patient, able to hold its inner warmth across spans of time that dwarf the history of life on Earth. It is a slow ember, cooling across the ages, in no danger of going cold while anything we know endures. There is a gentle thought in this. The storms we see on Jupiter, the great red oval, the racing bands, the lightning and the slush, are all in the end the visible signs of a planet slowly releasing the warmth of its own beginning. Every swirl of cloud is heat from the planet's birth, and from its endless settling, making its slow way out into the dark. The violence of Jupiter is, in this light, simply the long exhalation of a world cooling from its making, an exhalation that has lasted since before the Earth was formed and will continue long after. And this inner warmth points toward one of the most thought-provoking facts about Jupiter. The planet is made of the same material as the Sun, and it carries its own heat, and it is enormous beyond any other world around us. It came, in a sense, close to being something far greater than a planet. It came close to being a star. Why it never lit, and what it might have become if it had, is where we turn next. Jupiter is built from the same ingredients as the Sun. Both are made mostly of hydrogen and helium, drawn from the same great cloud that collapsed to form the solar system. In its broad recipe, Jupiter is a small piece of the Sun's own substance, gathered into a separate ball. This has led to a description of the planet that has lingered for a long time. Jupiter, it is sometimes said, is a star that failed, a sun that never managed to light. The phrase is not quite fair to the planet, but it points at something true. What makes a star shine is the fusion of hydrogen in its center, the joining of light atoms into heavier ones, which releases tremendous energy. This only happens when the pressure and temperature at the center of a body grow high enough, and that requires a great deal of mass. The center of Jupiter is hot, hotter than the surface of the Sun, but it comes nowhere near the conditions needed to fuse hydrogen. The planet is simply too small. Its gravity cannot squeeze its center hard enough to begin the reaction that powers a true star. The gap is not small. For Jupiter to become an ordinary star like the Sun, fusing hydrogen steadily in its center, it would need to be something like 80 times its current mass. 80 Jupiters poured into one would have a center crushed and heated enough to ignite. There is a lesser threshold as well. A body roughly 13 times the mass of Jupiter can fuse a heavier form of hydrogen called deuterium for a while, producing a dim, brief glow. Such objects are called brown dwarfs, the dim, failed stars that sit between planets and true suns. Jupiter falls below even this lower line, well short of the mass needed to glow by any kind of fusion at all. So Jupiter sits in a strange middle ground, far too large to be an ordinary planet in the way the rocky inner worlds are, yet far too small to be any kind of star. It has the recipe of a sun, but not the size, the composition without the mass. Had the early solar system gathered much more material into this one body, our sky might have held two suns instead of one, a bright sun and a dim red second sun glowing faintly where Jupiter now turns. Instead, the material ran short, and Jupiter became the greatest of planets rather than the least of stars. The planet most likely formed first among the worlds of the solar system. In the young disk of gas and dust around the newborn sun, a body began to gather beyond the line where ice could form, where there was a great abundance of material. This growing body built up a core large enough that its gravity could begin to capture gas directly from the surrounding disk. Once that threshold was crossed, it gathered gas quickly, pulling in an enormous envelope of hydrogen and helium before the young sun's light and wind swept the remaining gas away. Jupiter grew large precisely because it formed early enough to claim the gas before it was gone. This head start is why Jupiter is so dominant. It took the lion's share of the leftover material from the Sun's formation, far more than any other planet managed to gather. The worlds that formed afterward, including the other giant planets, had less to work with, and the rocky inner planets less still. Jupiter, by being first and by reaching the critical size soonest, became the great inheritor of the Sun's leftovers, which is why it holds more than twice the mass of all the other planets combined. Its dominance is a record of its early and rapid growth. There is a quiet poignancy in the idea of a body that came close to being a star and instead became a planet. Jupiter holds within it the same fire-making substance as the Sun, the same hydrogen that lights the sky. It carries its own warmth, glows softly with heat, and rules a system of moons like a small sun rules its planets. In almost every way but one, it resembles a star in miniature. It lacks only the mass to cross the final line, and so it has spent the entire age of the solar system glowing dimly with leftover warmth rather than blazing with light of its own. It helps to see where Jupiter falls along the full range of such bodies. At one end are the rocky worlds, like the Earth, small and solid underfoot. Then come the giant planets like Jupiter, great balls of gas with no fire of their own. Above those sit the brown dwarfs, bodies too large to be planets and too small to be true stars, glowing faintly for a time on a feeble kind of fusion before fading toward darkness. And beyond those begin the real stars, starting with the small, cool red dwarfs that burn slowly and steadily for ages. Jupiter sits well down toward the lower end of this range, a giant planet rather than any kind of star, separated from even the dimmest red dwarf by a wide gulf of mass. Yet the range is continuous, each kind of body shading gradually into the next, and Jupiter marks the place where a world grows about as large as a world can be, without beginning, however faintly, to shine. It is worth resting on that thought without sorrow. Jupiter is not a lesser thing for having failed to become a star. It is the largest and most powerful of the planets, the ruler of the greatest system of moons we know, the maker of the strongest magnetic field and the most enduring storm. It found a different kind of greatness from the one its composition seemed to promise. The star that never lit became instead a world unlike any other, and the solar system is the more interesting for it. And in its role as a small sun to its own family of moons, Jupiter does something a true star does. It shapes the worlds around it with its gravity, warming some and tearing at others, ruling their motions and their fates. Nowhere is this clearer than in the innermost of its great moons, a world so worked upon by Jupiter's pull that its entire surface is remade by fire. That burning moon is where we turn now. The innermost of Jupiter's 4 great moons is a world unlike any other in the solar system. It is roughly the size of our own moon, but where our moon is grey and still and ancient, this one is yellow and orange and red, and it is anything but still. It is the most volcanically active body we know of anywhere, its surface erupting and reshaping itself constantly. Hundreds of volcanoes dot its face. Lakes of molten rock glow on its surface. Plumes of erupted material rise hundreds of miles into space. This moon is on fire, and it has been for a very long time. The eruptions here are on a scale that dwarfs anything on Earth. Plumes of gas and dust rise as high as 250 miles above the surface, fountaining into the dark in great umbrella-shaped arcs before falling back. Lava spreads across the surface in great flows, and lakes of molten rock simmer in the openings of the volcanoes. The whole surface is repaved so often by these eruptions that it bears almost no impact craters, which on most worlds accumulate over billions of years. Here they are buried as fast as they form. The face of this moon is, in a planetary sense, brand new. What makes this small moon burn so fiercely when our own moon went cold and quiet long ago? The answer is Jupiter's gravity, working through a subtle arrangement of orbits. The three innermost large moons of Jupiter circle the planet in a precise rhythm, their orbital periods locked in a simple ratio, so that for every circuit of the outer one of the three, the middle makes 2 and the inner makes 4. This locked rhythm is a kind of gravitational resonance, and it keeps the orbit of the innermost moon from settling into a perfect circle. Because its orbit is held slightly stretched, the moon moves nearer to Jupiter and then farther away with each circuit, and the strength of Jupiter's pull on it rises and falls. This changing pull flexes the entire moon, squeezing and stretching its solid body by as much as 100 meters with every orbit. Bend a piece of metal back and forth, and it grows warm in your hands. The same thing happens to this moon on an enormous scale. The constant flexing generates heat by friction throughout its interior, melting its insides and feeding the endless eruptions at its surface. Jupiter, in effect, kneads the moon until it glows. This heat is entirely separate from the sun. So far out in the cold, sunlight could never melt a world. The fires of this moon are powered purely by gravity, by the gentle and ceaseless tidal working of Jupiter and the neighboring moons. It is one of the clearest demonstrations in the solar system that a world need not be near a star to be warm. Tides alone, given the right arrangement of orbits, can melt the inside of a moon and keep it molten across the ages. The most volcanic place we know of is also one of the farthest from the sun's warmth. The eruptions do more than reshape the moon. The gas they throw into space, much of it sulfur and its compounds, escapes the moon's weak gravity and is swept up by Jupiter's magnetic field. This is the source of the great glowing ring of charged particles that circles the planet, and a major source of the material that feeds Jupiter's radiation belts and its endless auroras. The burning moon is constantly breathing its substance into the space around Jupiter, losing about a ton of material every second to the planet's magnetic grip. The crown of light at Jupiter's poles is fed, in large part, by this single restless world. The moon pays a price for all of this. It sits within the worst of Jupiter's radiation, bathed in a lethal storm of particles, its surface scoured by an environment that would kill a human in minutes. It is constantly losing material to space. It is flexed and heated without rest, its insides churned into molten rock, its face erupting and repaving itself again and again. It is, in every sense, a world being worked upon by forces far larger than itself, caught between the pull of its giant and the pull of its neighbors, unable ever to come to rest. And yet there is a strange splendor to it. This is a world painted in the colors of sulfur, yellow and white and orange and red, its surface a shifting canvas of fresh eruptions and cooling flows. Its volcanoes glow in the dark. Its plumes catch the distant sunlight as they rise. It is a place of constant creation and destruction, never finished, never still, the most geologically alive body in the solar system. To watch it, if we could watch it closely, would be to see a world remaking itself in real time, lit from within by the fires that Jupiter's gravity keeps forever burning. Beyond this moon of fire lie its siblings, worlds that Jupiter's gravity also warms, but more gently. Where the inner moon is melted and erupting, the next worlds out hide their warmth below shells of ice, and beneath that ice they hold oceans of liquid water. Around the most lethal planet in the solar system, in the shadow of all that radiation, may lie some of the most promising places to search for life. We turn now to those hidden oceans. The next great moon outward from the burning world is one of the most intriguing places in the solar system. It is covered in a shell of ice, smooth and bright, crisscrossed by long cracks and ridges but almost free of craters. The smoothness is a clue. A surface without craters is a young surface, one that has been renewed. And on this moon, the renewing is done not by lava, but by water. Beneath the icy shell, this moon is thought to hold a global ocean of liquid salt water, and that ocean may contain more water than all the seas of Earth combined. The ocean stays liquid for the same reason the inner moon stays molten. This world, too, is caught in Jupiter's tidal grip, flexed gently as it orbits, and that flexing produces warmth inside it. The warmth is far less than on the burning moon nearer in, but it is enough to keep a great ocean of water from freezing solid beneath the ice. So here, far from the sun, in a place where the surface is colder than almost anywhere on Earth, there is liquid water, kept warm by gravity, held safe beneath a protective shell of frozen crust. Liquid water is the one thing life as we know it cannot do without. That single fact has made this icy moon one of the most compelling places to search for life beyond Earth. Beneath its ice lies a dark ocean, possibly in contact with a rocky floor below, possibly warmed by vents where heat and minerals seep into the water. On Earth, such places on the floors of our own oceans teem with living things that need no sunlight at all. Whether the same could be true beneath this distant ice, no one yet knows. But the ingredients we would look for, water and warmth and the right chemistry, may all be present in the dark. There is a quiet irony in this. Jupiter is the most lethal planet in the solar system, wrapped in radiation that would kill in minutes, and yet tucked among its moons, shielded beneath miles of ice, may lie some of the most promising places for life anywhere near us. The same tidal heating that turns the inner moon into a furnace gives the next moon out a warm, sheltered sea. The thick ice that covers the ocean also shields it from the worst of the radiation above. Around the great destroyer, in its very shadow, there may be cradles for life. The third great moon is the largest moon in the entire solar system, larger even than the planet closest to the sun. It is a world in its own right, big enough that if it orbited the sun directly rather than Jupiter, we might well call it a planet. This moon is remarkable in another way as well. It is the only moon known to generate its own magnetic field, produced by a churning of metal in its center, so that it sits like a small magnetic world within the much greater magnetic field of Jupiter. It, too, is thought to hide a salty ocean far below its surface, sandwiched between layers of ice. These three inner moons are bound together by the same gravitational rhythm, their orbits locked in the simple ratio that keeps them flexed and warm. They form a kind of graded series, a demonstration of what Jupiter's tides can do at different distances. Nearest in, the flexing is so strong the moon is molten and erupting. Next out, it is gentle enough to keep a warm ocean beneath ice. Farther still, the warmth is less, the ocean smaller or deeper down. The single force of Jupiter's gravity, working through these locked orbits, produces fire on one world and hidden seas on the next. It changes how we should think about where life might arise. We once imagined that a world needed to sit at just the right distance from a star, in a narrow band where water could be liquid at the surface. These moons suggest a different and more generous possibility. Far from any star, in the cold outer reaches, a giant planet's gravity can warm its moons from within and hold oceans beneath their ice for billions of years. If that is so, then the places where life might find a foothold are far more numerous than the sunlit surfaces of worlds. They may include the dark, warm seas hidden inside icy moons throughout the solar system and beyond. We do not yet know what lies beneath that ice. It may be only dark and silent water, lifeless and still. Or it may be something more. The question is among the most patient in all of science, because answering it will take great effort and great care, sending craft to these distant moons and finding ways to sense what lies far below their frozen shells. For now, the oceans keep their secret, turning slowly in the dark beneath the ice, warmed by the gravity of the giant they circle, waiting for an answer we cannot yet give. Beyond these warmed and watered moons lies the outermost of the four great worlds, a quieter place, far enough from Jupiter to escape much of the flexing and the radiation alike. It is an ancient, cratered world that has kept its record across the ages, and beyond it lie the faint rings and the small shepherd moons that complete Jupiter's family. We turn to those quieter members of the system now. The outermost of Jupiter's four great moons is the quietest of the family. It is a world of roughly the size of the planet nearest the Sun, and its surface is among the most heavily cratered in the entire solar system. Where the inner moons have had their faces erased and renewed, this one has kept its scars across billions of years. Crater lies upon crater, the record of countless impacts piled up over the long ages, undisturbed. To look at this moon is to look at one of the oldest unchanged surfaces near us, a face that has been gathering marks since the early days of the solar system. The reason for its stillness is distance. This moon orbits far enough from Jupiter that it escapes much of the tidal flexing that melts the inner worlds. It is not locked into the same tight rhythm of orbits, and so Jupiter does not need it as it needs the burning moon. Without that constant working, the moon never developed strong internal heat, and so it never resurfaced itself with fire or water in the way its siblings did. It simply formed, gathered its craters, and grew quiet, and quiet it has remained ever since. Its distance brings another mercy. This outermost great moon orbits beyond the worst of Jupiter's radiation belts, in a region where the lethal storm of particles has thinned to something far gentler. Of all the large moons, it is the one where a visitor might survive the radiation for a meaningful time. In discussions of where humans might one day place a base among Jupiter's moons, it is this quiet, distant, cratered world that comes up most often, precisely because it sits far enough out to be spared the killing light. Safety in the Jovian system means keeping your distance from the giant. Even this ancient moon may hide a measure of warmth far below. There are hints that beneath its battered crust, it too may hold a layer of liquid water, buried far deeper than on its livelier siblings and harder to detect. If so, it would be a still and quiet ocean, locked away beneath miles of ice, untouched by the flexing that stirs the inner moons. But much about this distant world remains uncertain, because it has been visited only in passing, and its outermost depths have never been sounded. It keeps its secrets in the cold, far from the giant's reach. Beyond the great moons, and far closer in, Jupiter wears a set of rings. They are not the bright, broad bands of ice that crown the next planet out, the ringed giant, whose rings can be seen from Earth through a small telescope. Jupiter's rings are faint and dark, made of fine dust rather than glittering ice, so thin and dim that they went entirely unknown until a passing spacecraft looked back toward the sun and caught them glowing in backlight. They are among the most delicate ring systems we know, a faint veil around the planet rather than a brilliant crown. The dust that makes these rings has a humble origin. Circling close to Jupiter, inside the orbits of the great moons, are several small, irregular moons, little more than mountains of rock. They are constantly struck by tiny meteoroids, and each impact knocks a puff of dust off their surfaces into space. That dust spreads into thin rings around the planet, continually replenished as the small moons are slowly worn away. Jupiter's rings are, in effect, the drifting dust of its smallest moons, ground off grain by grain and spread into faint circles by the planet's gravity. These small inner moons live in a harsh place, close to the planet and within the radiation, slowly eroding under the constant rain of tiny impacts. They are shaped irregularly, like potatoes or shards, far too small for their gravity to pull them into spheres. Yet they play their quiet part in the system, shepherding and feeding the faint rings, marking the inner edge of Jupiter's family of moons. Between these little inner shepherds and the four great worlds farther out, Jupiter commands a graded company of moons that ranges from dust-shedding fragments to worlds larger than planets. It is worth pausing on the sheer completeness of Jupiter's system. The planet is circled by more than 90 moons in all, from the four great worlds down through dozens of smaller captured fragments wheeling in distant, tilted orbits. It holds rings of its own dust, fed by its smallest moons. It warms some worlds to fire, and others to hidden seas, and lets the most distant grow old and quiet in peace. It is less a planet with a few moons than a system in miniature, a small sun ruling its own family of worlds, complete with its own gradations of fire and ice and stillness. All of this we have come to know only slowly, and only by sending machines across the immense gulf to look. The storms and the moons, the rings and the radiation, the metal ocean inferred from gravity, the hidden seas sensed through ice, all of it has been gathered piece by piece by the craft we have sent out toward the giant. Before we draw toward the close of our journey, it is worth remembering those patient travelers and how much care it has taken to learn what little we know. We turn now to the watchers we have sent. Almost everything we know about Jupiter beyond what a telescope can show has been gathered by spacecraft sent across the enormous gulf to study the giant up close. The distance alone is humbling. Jupiter lies so far away that light itself, the fastest thing there is, takes the better part of an hour to travel between it and the Earth. A command sent to a craft at Jupiter and the reply that comes back are separated by the better part of 2 hours. No one on Earth can steer a probe there in any immediate sense. The craft must largely look after themselves, so distant that even light grows slow on the way. The first machines to reach Jupiter only flew past. They crossed the great distance over years of travel, swept by the planet in a matter of days, and gathered all they could during that brief encounter before continuing onward into the outer dark. Even those passing visits transformed our understanding. They returned the first close views of the banded clouds and the great storm, the first clear sight of the major moons as distinct worlds, and the first discovery of the faint rings, caught in backlight as the craft looked back toward the sun. In a few days each, these flying visitors taught us more than centuries of viewing from Earth. Later came a craft that did not merely pass but stayed, settling into orbit around Jupiter to study it across years rather than days. This orbiter carried with it a small probe, which it released into the planet's atmosphere to fall and measure as it went. That was the probe whose hour-long descent we spoke of earlier, the one that reached only the thin outer skin of the planet before being overwhelmed. The orbiter itself circled Jupiter for years, studying the moons in turn, watching the storms change, and piecing together the workings of the system as no flying visit ever could. More recently, Another orbiter was sent on a bolder path, designed to study Jupiter from up close while surviving the radiation that destroys lesser craft. It loops over the planet's poles in a long, careful orbit, diving in close for a brief pass, and then swinging far out again, threading the gaps between the most lethal belts. With its electronics shielded inside a thick titanium vault, it has measured the planet's gravity and magnetism with great precision, sounded the depths of the Great Storm, mapped the polar cyclones, and revealed the smeared and uncertain center of the planet. Much of the most surprising knowledge we have of Jupiter has come from this single armored traveler. These missions demand a patience that stretches across human careers. A craft sent to Jupiter may take years simply to arrive, often looping past other planets along the way to borrow a little of their motion and gain speed. Once there, it may work for years more. The people who design such a mission may see it through from first sketch to final signal across the better part of their working lives. Teams pass knowledge from one generation to the next, tending craft that left Earth long ago. To study Jupiter is to commit to a slow kind of work, measured in decades, carried out by people content to plant something whose fruit comes long after. The radiation makes every moment at Jupiter costly. Each pass through the inner system adds to the damage done to a spacecraft's electronics, and so the missions are planned around the radiation as a sailor plans around a storm, choosing paths and timing that limit the exposure. There is a quiet bravery in sending our machines into an environment we know will slowly destroy them, knowing that each one has a limited life within the belts, and racing to gather all we can before the giant wears it down. The craft are, in a sense, sacrificed to our curiosity, given over to the radiation in exchange for knowledge. There is more still to come. Plans are underway to send craft to study the icy moons in detail, to sound their hidden oceans, and to learn whether those dark seas beneath the ice could hold the conditions for life. Reaching them means once again crossing the Great Gulf, enduring the radiation, and working with enormous patience across the years. But the questions are among the most compelling we can ask, and so we keep sending our watchers outward, each one carrying a little more of our attention to the giant and its family of worlds. And yet, for all we have learned, we have barely touched Jupiter. Every probe we have sent has sampled only the thinnest outer layers, the cloud tops, and the space around the planet. The metal ocean, the uncertain center, the great body of the world below the clouds, all of it remains forever beyond our direct reach, known only through careful reasoning and indirect signs. We have come to know Jupiter the way one might come to know an ocean, by studying only its surface and its shore. The planet keeps the greater part of itself hidden, and likely always will, no matter how many watchers we send. That hiddenness is a fitting note on which to begin our close. Jupiter is a world we can study, but never truly enter, observe, but never survive, a giant that has let us see its face and its moons, while keeping its center sealed away. Before we let it rest, there is one last role to consider, perhaps the most surprising of all. For this enormous, lethal, unknowable planet may also be one of the reasons that the Earth, so far away and so small, was ever quiet enough for life to take hold. We turn at last to Jupiter the shepherd and to the strange gift of its presence. Jupiter's power does not end at its magnetic field or its family of moons. Its gravity reaches across the whole solar system, and by the simple fact of its enormous mass, it governs the motion of countless smaller bodies. Comets and asteroids that wander near it feel its pull and have their paths bent, sometimes gently, sometimes drastically. Jupiter is the great traffic controller of the solar system's small bodies, the largest gravitational influence after the Sun itself, and its hand can be felt far beyond the reach of its storms. The asteroid belt between Jupiter and the inner planets bears the clear mark of this influence. Jupiter's gravity has carved that belt into a structured place, opening gaps where its pull would tug an asteroid too strongly, and shepherding the remaining bodies into stable zones. Without Jupiter, the belt would be a very different region. With it, the asteroids are sorted and herded, their orbits shaped by the steady tug of the giant, kept from gathering into a planet of their own. The belt is, in a sense, a planet that Jupiter never allowed to form, scattered into rubble by its overwhelming pull. Locked into Jupiter's own orbit are two great swarms of asteroids, one riding ahead of the planet and one trailing behind. These are held in place by a balance of gravity between Jupiter and the Sun, gathered at two stable points along the planet's path, where objects can sit without drifting away. There are many thousands of these companions, traveling around the Sun in step with Jupiter, escorting the giant on its long circuit. They are a quiet retinue, swept up and held by Jupiter's gravity over the ages, marking the special points along its orbit where stability reigns. Jupiter's pull also reaches out to the comets that fall in from the outer solar system. Some of these icy travelers, on plunging toward the Sun, pass near Jupiter and have their paths reshaped by its gravity. The planet can fling a comet away, or bend its orbit, or capture it into a new path. On occasion, it does something more final. Once, a comet that wandered too close was captured by Jupiter and pulled into orbit around it, and the planet's powerful tides tore the comet into a chain of separate fragments, strung out like a line of beads. Over several days, one after another, those fragments fell into Jupiter and struck the planet. The impacts left their mark plainly. Each fragment, plunging into the atmosphere, blasted out a dark scar larger than the Earth, and those scars lingered in Jupiter's clouds for months afterward, slowly fading as the winds carried them away. It was the first time we had ever watched one body in the solar system collide with another in real time, and Jupiter was the stage on which it happened. The event was a reminder of the planet's role as a gatherer of debris, pulling in wandering objects and absorbing them into itself, scarring and healing across the seasons. This role has long been described as a kind of shield. By drawing in or deflecting comets and asteroids that might otherwise reach the inner solar system, Jupiter may have reduced the number of large impacts on the inner planets, including the Earth. The true picture is more nuanced than a simple shield, for Jupiter's gravity can also fling objects inward as easily as it can deflect them, and the balance of help and harm is still studied. But there is little doubt that Jupiter has profoundly shaped the traffic of small bodies through the inner solar system across its history, for better and for worse. The giant's influence reaches back to the very arrangement of the planets. In the early days of the solar system, as Jupiter formed and moved through the young disk of gas, its gravity likely shaped where the other worlds ended up. It may have limited how much material the planet Mars could gather, leaving Mars small. It helped sculpt the asteroid belt into its sparse, structured form. Its movements may even have influenced the delivery of water to the inner planets, helping to steer icy material toward the worlds where oceans would one day form. The story of how the inner solar system came to be is, in part, the story of Jupiter's early wanderings. This means that the Earth's own existence is bound up with Jupiter in ways we are still untangling. The size of our neighboring worlds, the structure of the belt that lies between us and the giant, the history of impacts our planet has endured, perhaps even the arrival of some of our water, all carry the fingerprints of Jupiter's gravity. The most lethal planet in the solar system, the one place above all others where nothing could survive, may also have been a quiet shaper of the conditions that let life arise on the small world where we stand. Its presence has been woven into our story from the beginning. There is a fitting symmetry in this. Jupiter destroys without effort and shelters without intent. It gathers comets to itself and tears them apart, and in doing so may spare worlds further in. It governs the asteroids and shaped the planets, indifferent to the consequences, and yet those consequences may include the very quiet that allowed us to come into being. The giant is neither guardian nor destroyer by any will of its own. It is simply enormous, and its mere existence across the long ages has helped to set the stage on which everything else has played out. And so we come to the end of our long passage through this world, having fallen through its storms and its crushing layers, having stood in imagination within its lethal light and beside its tormented moons, having traced its invisible reach across the whole solar system. What remains is to step back one last time and see the giant whole, turning quietly in the cold, and to let it go. We turn now to that final view and to rest. We have traveled a long way into this world tonight, and it may help to gather it all into a single quiet image before we let it rest. Jupiter is the largest planet the Sun has ever made, a globe of hydrogen and helium more than 300 times the mass of the Earth, turning so fast that a day there lasts under 10 hours. It has no ground anywhere, only a long fall through thickening fluid toward a center hotter than the surface of the Sun. It is the most extreme world we know in nearly every measure, and nothing we are could survive even its outer edges. Everything about the planet runs past the limits of what life can meet. Its storms are wider than the Earth and last for centuries. Its winds blow for years without tiring, fed by a warmth that has been leaking out of it since before our world was solid. Its magnetic field is the strongest of any planet, carving out an invisible structure larger than anything else around the Sun. Within that structure lies radiation fierce enough to kill in minutes and to wear down even our most armored machines. To call Jupiter unforgiving is only to describe it plainly. And yet, when we look at the planet honestly, there is no malice in any of it. Jupiter does not threaten us. It does not reach toward us or wish us any harm. It is simply very large and very old, and built entirely out of conditions that happen to be lethal to small, soft creatures like ourselves. Its hostility is nothing more than its nature, the ordinary nature of an enormous ball of hydrogen turning in the cold. The danger we feel when we contemplate it is real, but it is the danger of a place we were never meant to go, not the danger of anything that means us ill. There is even a kind of gift hidden in this giant. By its gravity, it has shaped the solar system we live in, herding the asteroids, gathering the comets, helping to arrange the worlds and perhaps to steer water toward the inner planets long ago. The most lethal place we know may have helped, in its indifferent way, to make our own small world quiet enough for life. The same giant that would destroy us in an instant if we drew near has, across the long ages, been part of the reason we are here at all. It is destroyer and shaper at once, and it knows nothing of being either. It helps to remember how long Jupiter has been doing all of this. The great storm was already turning before there was anyone to see it. The auroras have been glowing at its poles through every moment of human history and through the long ages before. The planet was here, enormous and complete, before the Earth had cooled, before the first ocean, before the first living thing. It has presided over the solar system in silence the entire time, asking nothing, needing nothing, simply turning. It will go on turning, just the same, long after this night and every night like it has passed. There is something steadying in that thought, rather than something fearful. Out there in the cold, a world larger than 1,000 Earths is turning slowly through its storms, exactly as it has for billions of years, entirely untroubled by anything that happens here. It does not need us to watch it or to worry over it. It does not need anything from us at all. Its great storm will keep its slow rotation, whether we are awake or asleep, whether we are here or long gone. The giant carries on, indifferent and immense, and that indifference is its own kind of peace. So let the giant turn where it has always turned, far out in the faint light, wrapped in storms it will never feel, and crowned in fires no eye will ever need to see. There is nothing here you have to hold on to, nothing you need to carry into the night. The largest world the sun ever made will keep its slow vigil without you, as it always has. You are free to set it down and let it drift away into the dark where it belongs. Let your breathing slow now, as gentle and unhurried as the turning of that distant world. Let your thoughts grow as quiet as the space between the stars. Let the weight of the day loosen and fall away, the way a storm fades into a calm band, the way a comet's scar heals slowly into clear sky. There is nothing left to do tonight but rest. The giant is turning, the auroras are glowing, the moons are circling in the dark, and none of it asks anything of you. Sleep well, and good night.